Okay, so this is the last of the review that we're going to do because this is chapter 20. This is the last one that College Board usually considers to be important for AP, so we're not going to worry about reviewing nuclear and organic, plus they were the most recent ones we did. So let's go back and review Electrochem, which is chapter 20. So back in chapter 4, we already did standard redox reactions. We already did the advanced redox reactions. We already handled the first two parts of chapter 20. So the next part of chapter 20 then is talking about voltaic cells. So voltaic cells are the idea that we already know from redox that we're transferring electrons from one element to another, one atom to another, or several atoms to several other atoms, and that the number of electrons that are lost by one group of atoms has to equal the same number of electrons gained by another group of atoms. So we already got that worked out. So now it's the understanding that there's a force or a potential behind those electrons actually moving from one to the other. And that potential is related to electronegativity. It's related to the force of the nucleus pulling on electrons, right? That kernel charge or that force that's going to attract them. And therefore, we refer to it as a potential for the electrons to move, which is our voltage. So when we're talking about voltage, we're talking about joules per coulomb, right? Joules per charge, right? So we know what the charge of electrons are, so we can go look up what a coulomb is, or what the charge of electron is in coulombs. And so what this is telling us is that the potential for electrons to move is related to how much energy the electrons have and how much charge we're trying to move, or how much energy per each charge that is trying to move. So voltage can be misleading sometimes because high voltages might not be dangerous to you because you could have a really, really high energy, but no charge actually carrying that energy, like a static charge, right? I could have an arc come out of my finger, static electricity, that could be 10,000 volts, but it might only be 3 electrons. So yeah, it was 30,000 joules, but it was only 3 electrons. So how much damage is it really going to do? But you can have a current coming out of the electrical outlet that's only 120 volts, and that would kill you because of the fact that the number of charges that are pouring out of that outlet as it's passing through you is a huge amount. So even though the energy per each charge isn't as high, there's so much charge coming through that now it's enough to be dangerous to you. So voltage doesn't necessarily give us the indication of how dangerous something is. The thing that gives us the indication of how dangerous something is the current. The current is in coulombs per second. This is how much of that charge is going to enter you or pass by you in a second, right? This is the one that you worry more about because this is talking about how much charge is actually flowing. So this is telling us how much energy is in each charge. This is telling us how much charge is flowing. And then we can start to figure out how dangerous that is going to be for us. All right, so how do we use this to our advantage? Well, we have an energy component here. So if we can get electrons to start moving, it can start providing energy for things, right? And the more electrons we can get moving, the more energy we can generate. So how do we get these electrons to move? Well, the answer is we take our two halves of our chemical reactions, and instead of having them happen right next to each other or mixed up together in a container, we can separate them into 2 separate containers, and that will have to force the electrons to travel. Okay, so here we go. Put a cell over here and put a cell over here. All right, so we have a half cell on one side. We'll do the typical copper and zinc one. So I'm going to put zinc in over here, and then I'm going to put it in a bath of zinc ions. And then over here, I'm going to put copper in a bath of copper ions. All All right, and then I'm going to connect them to a voltmeter. All right, so we can see how much potential there is for these electrons to move. So we're looking at that voltage. And right now it would read 0. And the reason why it's going to read 0 is because you aren't actually having electrons transfer completely from one electrode to another. Electrons actually move really, really slowly through wires. It's the field that is created by this that causes the electrons to move. But it's not just the electron from here getting to there. What it actually does is it causes all the electrons to move simultaneously. You know, we talked about how metals don't hold on to their valence electrons very well, so therefore all those valence electrons can start to flow in one direction. So yeah, an electron might jump into the wire on this side, but we're not going to wait for that electron to get all the way through the wire because that would take hours. What we're going to do is we're going to let an electron jump in this side. All the electrons in the wire move to accommodate the fact that that electron's coming in, and then an electron on this side comes out and goes into the metal. But that can't happen if we start building up charge. If I was to do this, we'd see a voltage and it would go right back to 0. And the reason is because if all the electrons move and this becomes negative and this becomes positive, now all the electrons are going to want to move back because they don't want to build up charge. It's not just going to build up a whole bunch of negative charges here just because. So what we have to do is we have to make sure that we set this up to be a complete circuit so that some charge can go back to balance it all out. So how do we do that? Well, that's what our salt bridge is. So our salt bridge is usually made up of potassium nitrate. Potassium nitrate, because potassium and nitrate is not going to ever get involved in redox reactions when you're dealing with water. They're just not going to be active enough and create a voltage that's going to be greater than the things that are already in there. So it's like the perfect salt to use for this because it has almost no effect on anything else that's happening in there. All right, so let's look at how the potassium nitrate plays a role here. So when we do this, what it turns out to be is that copper is less reactive than the zinc, which means that the zinc is better at giving up electrons than the copper is. So the copper is more likely to take in electrons because of its electronegativity, and zinc is more likely to dump electrons, which means that electrons are going to start to flow out of here, and electrons are going to start to flow into here. When the electrons flow into here, as I said earlier, this starts to make this negatively charged. Well, if this becomes negative, then the copper flows this way. The copper ions will pick up those negative charges, and you'll start to see the size of this get bigger because the copper ions are going to start coming out of solution in order to pick up these electrons and become copper metal. So what's happening over here is you have copper ions plus electrons making copper. All right, so this is our reduction. And reduction happens at the cathode. So this is our cathode side. Okay, now over here, the zinc is, well, let's finish the other side first. The copper is coming out of solution, which means that you're losing your positive charge in the solution. So how are we going to get that charge back? Well, the answer is your potassium ions that are positively charged are going to go and start to fill that side to make up for the positive charge that was lost to that side because the copper ions are reducing to become copper. So the potassium ions are going to travel that way to keep the charge over here neutral. That's the goal of the salt bridge ions, is to keep the charge neutral in the two halves. All right, so over here, the electrons are being pulled out of the zinc metal, which means that this zinc is losing electrons. So it's zinc equals zinc ions plus 2 electrons. And so if that's happening, it means that this is going to start to make more zinc ions in solution, and over time, this electrode is actually going to get smaller. All right, so this is happening. You're releasing electrons. So this is oxidation. And this is happening then at the anode. All right, so what's happening here is we're building up more positive charge on this side, which isn't okay. So how are we going to counter that? Well, the nitrate ions are going to start moving that way to help stabilize the charge over here and balance it to keep this side neutral. So the idea of the ions in the salt bridge is to move and take the place of the things that are being changed so that the charge in each side stays neutral so that the whole circuit can completely keep running without having any resistance, anything pulling back on it and making it go backwards, right? So both of these things have to be happening, or all of these things have to be happening simultaneously. So how do we read this voltage? Well, there's a certain potential for the copper to gain or lose electrons, and there's a certain potential for zinc to gain or lose certain electrons, and we find those potentials by comparing them to hydrogen. So we chose hydrogen to be our zero value of hydrogen gas turning into hydrogen ions or vice versa. That's our zero. And so if you put that on one side and any other electrode on the other side, you can see the potential of just that substance. All right? It was sort of arbitrarily chosen that we did that with hydrogen, but we did that because it's in water. We want to see the potential outside of water anyway. So that's kind of why we did that. But in the end, we go look up what the reduction potential is of zinc, and then we go look up what the reduction potential is of copper. And when you add them together, then you'll get the total voltage of the whole thing. But you can't just add the reduction potentials together. Let me get the numbers real quick so I can give you an idea. All right, so copper's reduction potential, which is what it did here, is 0.34. All right, that's the reduction potential. And zinc's reduction potential equals negative 0.76 volts. All right, but zinc didn't reduce. Zinc oxidized. So if zinc's reduction potential is negative 0.76, that means its oxidizing potential is plus 0.76, right? And now to get the overall potential, we just go 0.76 plus 0.34, and we get a total of 1.10 is the voltage for this cell. All right, I know they tell you the crazy thing where they go take the reduction from the cathode and minus the reduction from the anode, and that gets you the cell potential. It's exactly the same thing I'm saying here. You're taking negative the reduction of the anode because it's not reducing, it's oxidizing. And so you just switch the number and add them together. Don't memorize an equation. Just take the reduction potential and look at it and match it up. This is what the equation would be for the reduction potential, so we can take that number as it is. This is not what the equation would be for the reduction potential, so when we take the reduction potential equation and reverse it to make this, we just change the sign, and then we just add them together. And so that's how you can find the voltages for these and any cell. Okay, so they can ask you all sorts of cells. This is all voltaic cells or electrochemical cells. They love asking questions about the salt bridge. Just remember that whatever ions you're gaining or losing, the salt bridge is putting in the opposite charged ions to keep it neutral. And then your electrons are always going to flow from your anode to your cathode through the wire. And that's how you figure out your voltage from that. All right, so there is the first half of that chapter. So let me get rid of that. All right, other things it talked about is your relationship between this and free energy. So delta G equals minus NFE. All right, so now that you know what the potential is for the reaction to occur, that's what your E value is here, right? This is your cell potential. The F is the Faraday constant, which is the charge per mole of electrons. Instead of looking at the charge of one electron, it's the charge per mole of electrons. So all we did was take the charge of one electron and multiply it by 6.02 times 10 to the 23rd, and you get that 96,485 coulombs per mole of electrons. All right, we have our voltage here. And then N is your moles of electrons. So when you have your balanced equation, it's how many electrons were actually transferred. That's the value you're going to put in here for N. So on our previous example with copper and zinc, N is 2 because we have 2 moles of electrons being transferred. Every 2 moles of electrons that leave the copper or leave the zinc go into the copper. So that's where the N comes from. So you take your coulombs and you multiply by your voltage, and you end up getting your joules or your kilojoules for your delta G. And of course we know that delta G has to be negative, so this negative sign here will make it negative, but only if your cell potential is positive. So what you just learned is that if you have a positive cell potential, then you have a spontaneous process and the electrons will flow and it will work if you set up your cell with the salt bridge and all that stuff. But if your voltage that you come up with for your cell is negative, then it's not going to happen unless you force it and put on some sort of power supply to make it go the other way, which is exactly what we do when we do electrolysis, is where we provide the energy to cause a non-spontaneous electrical reaction to occur. Examples of electrolysis would be plating out of metal that normally would not want to come out of solution, let's say, or having sodium chloride salt as a solid be broken down into sodium and chlorine gas. That's not going to happen very regularly, and it certainly isn't going to happen when you have water around, because sodium is going to immediately react with the water and be sodium ions. And that's why when you want to make your pure elements from some of those salts like sodium chloride and potassium nitrate and aluminum stuff and all of that, you have to run electrical currents through it. And it has to be the salt, melted, molten salt, because if you have water present for any of those things, the water actually is more likely to oxidize and reduce than the ions are. So therefore, that wouldn't work, right? You don't want the water to become part of your cell. It can happen, and it's very likely to happen in a lot of cases. So when you're doing electrolysis and you're looking at that, you need to look at what their potentials are for water to oxidize and reduce and compare that with the potentials for your other ions to oxidize and reduce to see which one would really do it. So like for sodium chloride, water is going to oxidize instead of the water is going to reduce instead of the sodium reducing, and therefore you're never going to get the sodium ions out of solution, right? And have it turn into pure sodium in water. So this then will tell you whether or not your reaction will be spontaneous and therefore be a good battery and those sorts of things. All right. I'll come back to electrolysis in a minute. What if we have where we're not at equilibrium or we're changing any conditions? Because this all works when you have that E0, we're talking with 1 molar solutions. So what if we don't have 1 molar solution? So what if we're not at 1 atmosphere of pressure? So we have now situations where we might be or might not be at equilibrium. So we have the Nernst equation. All right, so we have our standard cell potential then ends up being RT over NF natural log of K when you start bringing in your delta G, and you know that that's equal to minus RT LMK, and so when you go and figure this all out, you end up with this, right? Because delta G can be equal to both of those things. You can derive this equation from it. So RT over F is going to be a constant under standard conditions, And so RT over F will all turn into this 0.0592. But then if we're not at equilibrium, then we're going to have that E0 value that we get from this, right? Because that's your delta G0. And then you have to have your quotient here, and there's your potential now, your new potential for the cell, not at standard conditions, right? So now we start looking at, well, what is our equilibrium here, and what does it tell us about it? And it really is quite simple. You can go calculate this mathematically, but you want to realize that when you do this, you're always going to end up with your fraction here, and your fraction is still going to end up being products over reactants. So if we go back and we look at our copper ions plus zinc metal yields zinc ions plus copper metal, what you'll realize from this is that your product is your zinc ions, which were being formed because it's being oxidized at the anode. So they always say anode on top, and then your copper is being reduced, but the only place that you have copper ions, which would go into equilibrium expression, is on the left side. So that's going to end up being on the bottom as your reactant, but that's what's happening at the cathode. So they always say it's anode over cathode, but you can see that right from your balanced equation that it's going to be anode over cathode. So what you want to look at then is where is your concentration greater, and what's that going to do? If your anode is greater than your cathode, meaning your Q is greater than K, then what's going to happen is it's going to make this negative bigger, which is going to cause your voltage to go down, which means I have too much product. Oh, too much product means it's going to shift back towards the reactant side. Well, your voltage is going to go down when it does that, and that's what this is saying. And if I have too much reactant, too much on the cathode side, then it's going to shift it towards the products, which is going to make this end up being more positive and add to it, and therefore my cell potential is going to go up, which should make sense because it's going to push it forward. So you can still think Nernst in terms of Le Chatelier and be fine. So you can answer all these questions with Le Chatelier, or you can show mathematically how Nernst applies. All right, so when we're talking about then electrolysis, you just have to acknowledge that you have multiple things in your solution, and that water is something that's always in there along with your other substances. So if it's in a solution, water solution, obviously if it says molten salt, you don't have to worry about water. But if water is in solution, now you have to start to think about, well, what is water going to do? What's its potential versus the potential of the other things in there? One of the things that people like to do is they like to electrolyze water so that you end up with hydrogen ions and oxygen ions. You end up with hydrogen gas and oxygen gas, right? You're trying to pull that out of your water that's in the solution. And so you should get twice as much hydrogen as oxygen. So you have to think about the fact that, okay, I have water in here, and water can oxidize or reduce to make my hydrogen and my oxygen, if you're thinking of the water in terms of hydrogen ions and hydroxide ions, which is how we see them in the cell potential tables, right? We're trying to get the hydroxide ions to produce the oxygen for us and the hydrogen ions to produce the hydrogen gas for us. All right, well, in the process of all of this happening, we're going to need some sort of salt in the solution to act like the salt bridge. You know, the most common one that people think of is, oh, I can do this at home if I do this with sodium chloride, and I have sodium ions and chloride ions. But the problem is that the sodium will actually not get involved in the reaction. As we stated earlier, water is more likely to reduce than sodium is, or the hydrogen ions are more likely to reduce than the sodium ions. So this won't reduce, but the chlorine will oxidize faster than the hydroxide will in the formation of the oxygen. So instead of getting the oxygen, you get chlorine gas, and then you die because chlorine gas is a poison. So what you have to do instead is you have to pick salts that don't oxidize or reduce easier than water does. So a common one to pick would be like potassium sulfate. Because just like sodium, potassium, you can use sodium sulfate too, but just like sodium, potassium will not reduce before the water will, and the sulfate doesn't get involved in these reactions very well at all, just like the nitrate. You have to have really strange reactions before the nitrate and the sulfate get involved. Like really strong concentrated solutions of those things with metals that don't really want to oxidize. So that's why we use like really strong nitric acid when we put it into the brass casing to get the copper out of it and all of that. That was a redox reaction where the nitrate actually got involved in it. They are very, very rare, especially in this course. So you have to use a salt that water is going to choose over the salt. But then the opposite's also true. If you have a salt solution and you want to get the salt out or get the salt turned back into elements, you have to make sure that the salt that's in there is going to oxidize and reduce easier than the water that's in there. So always be thinking, if it's a solution, about the fact that you have the water in there and what its potentials are before you do electrolysis. So electrolysis is we have to put the energy in. It's non-spontaneous in the forward reaction, so we put a power source on there to force the electrons to go in the direction they don't normally want to go. And in the process of doing that, we can cause things to oxidize and reduce that would not do it spontaneously. And that's really the whole concept of electrolysis. We don't really need to do anything deeper than that. So I think that will wrap up chapter 20.